Hi, my name is Yifei from Stony Brook University. I'm going to talk about our work, model checking support for file system development. This is the work in collaboration with Nimble Research and Harvey College. I will present the first half of the talk, and my colleague Weisu will present the second half. Developing and maintaining a file system is time-consuming, complex, and error-prone. It requires many years of effort and careful implementation, and should be compliant with specific standards like POSIX. However, even the popular and long-lived file systems, bugs are constantly emerging every year. For example, ButterFS was designed 14 years ago, still reported 110 bugs solely in 2020. Likewise, bugs were emerging for ext4, XFS, and other file systems. The file system bugs have serious consequences such as data loss, system crashes, and data corruption. File system bug detection is a well-studied area which can be applied to assist file system development. We created a similar table with Gerard to summarize 4 types of work that detect file system bugs. Regression test suites run fixed test cases, but they cannot cover sufficient corner cases and new features. Fuzzing generates invalid or random inputs to reveal bugs. However, fuzzing either detects the limited type of bugs, for example, memory safety bugs, or requires human effort to design and implement checkers, making these techniques less convenient for assisting file system development. Machine verifiable file systems were rigorously verified regarding some aspects of a file system, like crash consistency, but they cannot be applied to existing file systems directly. Model checking verifies if the specification holds the model of a system. Existing model checking work was limited to certain bugs, for example, crash consistency bugs, or required an abstract model for file systems. But the file system model is difficult to build because file systems are complex and continuously evolving. To address the limitations of existing approaches and assist file system development, we proposed a new model checking framework, MCFS, to test file systems thoroughly and effectively. MCFS has 5 design goals. First, we want to explore the state space of file system thoroughly and check many corner cases. Second, unlike other model checking work, MCFS eliminates the need for building an abstract model. MCFS should not change the behavior of the file systems under investigation and avoid observer effects. Ideally, MCFS should support a wide range of file systems, including user space, internal, and distributed file systems. Finally, MCFS should have high performance. The basic idea of MCFS is that we run multiple file systems concurrently and perform the same file system operations, that is, system calls. Then we check if all the file systems have identical states. MCFS consists of 4 components. Randomized test engines are the driver processes. We use a dual loop to issue non-deterministic system call sequences to each tested file system. We use the spin model checker to perform optimized state-space exploration for a given set of system calls and parameters. Integrity checks verify that all tested file systems have identical states by asserting the equality of return values, error codes, file data, metadata, and directory structure. Integrity checks report a potential bug if they find any discrepancy. Abstraction functions convert concrete states into abstract states, eliminating information that is not of interest to us. Next, my colleague Weisu will present the rest of the talk.
Thank you, Yifei. Hi, my name is Weisu. I'll discuss the challenges we encountered when developing MCFS and how we addressed them. We mainly met 3 challenges: state explosion, false positives, and cache incoherency. Spain compares the states in a byte-to-byte manner to tell whether a state has been visited. This will cause state explosion because any small change to the file system image will lead to a new state, even though logically the file system didn't change at all. For example, ext4 updates its timestamps in the superblock on each mutating operation, even if it didn't actually make any change. The consequence is that state exploration will never complete because the state space keeps growing with every noisy change. To address this problem, we define abstraction functions to calculate abstract states of the file systems. The abstract states, instead of the file system images themselves, will be used to distinguish unique states. It only considers directory structure, file content, and important metadata in the file system, and ignores noisy attributes such as timestamps. Another challenge was false positive. False positive means different file system behavior that should never be considered as bugs. We mainly encountered 4 types of false positives. First, different file systems may report size of directories differently. Second, the ordering of directory entries depends on the file system implementation. Third, some file systems have special folders, such as lost and found in ext4, whereas others don't. Last, different file systems expose different file data capacity, even though they are formatted on same-sized devices. We applied several techniques to prevent MCFS from terminating due to those false positives, such as ignoring attributes, sorting directory entries, excluding special folders, and equalizing free spaces. The last and the most significant challenge was cache incoherency. Spain needs to checkpoint and restore the states of the file systems when exploring the state space in breadth first or depth first search order. However, Spain cannot track the in-memory states of the file systems. For kernel file systems, Spain is a user space program and cannot access kernel memory. For fuse file systems, Spain cannot track their in-memory states either because they run in independent address spaces. Initially, we only had Spain track persistent states, but as a result, the file system became corrupted during experiments because of the incomplete state restoration. Then we developed 2 solutions. One is to mount and unmount the file systems before and after executing each operation. This will ensure coherency of in-memory states, but is slow and may hide bugs related to in-memory states. However, this approach is compatible with all existing on-disk file systems. The other solution is to provide the checkpoint and restore API in the file systems. This approach is efficient but requires implementing the API. To demonstrate the checkpoint and restore API, we developed an in-memory file system called VaryFS. This figure shows the architecture of VaryFS, and the green box highlights the checkpoint and restore API. The API comprises 2 ioctls. When Spain calls the checkpoint API, VaryFS saves the current concrete file system state in the snapshot pool. When Spain calls the restore API, VaryFS retrieves the appropriate snapshot to restore the file system state. Snapshot pool is a key value store for historic file system states. We developed 2 versions of VaryFS. VaryFS 2 uses more sophisticated data structures and supports more POSIX operations. Now let's look at the performance of MCFS. This figure shows the average file system operation rate of MCFS, shown in x-axis in log scale. We experimented with several file system pairs and various backend storage devices, as shown along the y-axis. For the ext2 versus ext4 experiment, using a RAM disk was about 20 times faster than using hard disk or SSD. This shows the benefit of using RAM as MCFS underlying storage device. The experiment was also 10 times faster than ext4 versus XFS because ext4 versus XFS used up memory quickly and began to swap. The VeryFS1 versus VeryFS2 experiment was 6 times faster than ext2 versus ext4 because of the efficient checkpoint and restore API and not having to mount and unmount the file systems. When developing VeryFS1, we ran MCFS to check VeryFS1 versus ext4. We found that VeryFS1's content differed from ext4's at some point. It turned out that VeryFS1 failed to zero out the new space if truncate method expanded the file. When developing VeryFS2, we checked VeryFS1 versus VeryFS2. We found that VeryFS2's content differed from VeryFS1's after performing write operations that extended the file's size, thus creating a hole. VeryFS2 failed to zero out the hole. MCFS discovered these discrepancies, allowing us to easily fix these bugs. In conclusion, we proposed MCFS, a new model-checking framework for file system development that can explore state spaces thoroughly and cover as many corner cases as possible. We developed VeryFS1 and 2 with checkpoint and restore APIs. The APIs enabled MCFS to efficiently track the full state of a file system. While developing VeryFS, MCFS found real bugs and considerably boosted file system development. As future work will add the checkpoint and restore API to Linux VFS, thus eliminating the need for unmount and remount. We will also run more than 2 file systems and apply inversion programming. Finally, we'll take advantage of swarm verification to perform model checking in parallel. Please see our MCFS paper for further details. That's the end of our presentation. Thanks for listening.